Okay, so the question that I had the most trouble with was actually problem number 1. Here's what the question stated, along with a diagram that we had to refer to. And I actually redrew the diagram over here. So what it was asking was to figure out how much deflection occurred. In order to do that, we had to apply the loop rule. And here you can see it applied right here. So the first equation was 2 EMF minus ILRL. This is based off of the long bulb, and you use the same concept for the round bulb, showing how much current is flowing. And set equal to 0, and then you solve for the resistance. You use ILRL based off of this equation, V equals IR. Now, the resistance will come in handy in the next part. So now you apply the loop rule once again, 2 EMF minus I2 RL, and then 2 EMF minus I3 RL. So this is I2, I3. Okay? And then you know that I1, based on the node rule, the current in is equal to the current out. That's how you get this, where I1 is equal to I2 plus I3. Now once again, you solve these equations. Like I had said earlier, the resistance is going to come in handy later on. This is the part where it's going to come in handy. So you plug in these resistances that you found into here, and you get this equation. See? And now you simplify it further, and you get 2 EMF times 1 minus I2 over IL is equal to 0 for the long bulb, and then for the round bulb you get 2 EMF times 1 minus I3 over IR is equal to 0. This tells us that I2 is equal to IL, and I3 is equal to IR. Using that concept that we just figured out, we plug it back into the node rule equation, and we figure out that since I1 is equal to I2 plus I3, that means I1 must also equal to IL plus IR. Now that we know that I2 is equal to IL, we can apply this concept, which I had written earlier, which is that the magnetic field of the wire is equal to the magnetic field of the earth times tan theta. Now we know that the magnetic field of the wire is proportional to the current, so that means that the current is proportional to the magnetic field of the earth times tan theta. Using that, we get magnetic field of the earth times tan theta 2 is equal to magnetic field of the earth times tan theta L. That means these cancel. This and this cancel, and you're left with theta 2 is equal to theta L. That means theta 2 is equal to 4 degrees, which was in the problem statement. Same concept applies to I3 is equal to IR. Once again, the same concept. That means theta 3 is equal to theta R. So theta 3 is equal to 15 degrees. Once again mentioned in the problem statement. Now this is where things change. I1 is equal to IL plus IR. So that changes our equation to the magnetic field of the earth times tan theta 1 is equal to the magnetic field of the earth times tan theta L plus tan theta R. These were determined earlier, right here. So using those, we plug it in, and we get 18.67 degrees deflection. So now, using these degrees that we have found, we can determine where the deflections occur. So 18.7 degrees is right here. I'll rewrite it. 18.7 degrees. 4 degrees. 15 degrees, and once again 18.7 degrees. Now the question is, what is the direction? So we know that this is going from negative to positive, so that means there's negative surface charges all along this wire, like so. Sorry, these are positive. And so on. So that means that this, since this is positive, and I forgot to denote, but this is north. So this is, these are negative, that means the deflection would be in this direction. 18.7 degrees in this direction. And once again, we have negative surface charges here and here, so it'd be in this direction. So to the northeast. And since this is positive, the opposite of negative, this would be deflected in the opposite direction, northwest. That's the solution to this problem. It's actually pretty simple. But yeah.